Oh, yes.
We did domain and range last time, didn't we?
Yes.
So now we're on to types of mappings.
Yeah.
Types of
Type
mappings.
map.
Yeah.
That's one of one. We do this next.
Okay. Yep. You'll need to write some definitions down. So
What's that?
a mapping takes.
What is mapping?
I'm explaining that.
Oh.
A mapping takes. Okay. A mapping, we'll call it F. A mapping F takes an element X from a set A and returns an element Y from B. And you write it like this. So what you're saying is, you can picture it like this. This is set A. This is set B. This is X, and X gives you Y if you calculate f of X. I'll give you an example in a moment. Yeah? Example. So let's say we have F and it goes from A, B, C, let's say, to D, E, F. And you can write it like this. Here is A, B, C. And here, D, E, F. And maybe A goes to D, maybe B goes to F, maybe C goes to F. So this means F of A is equal to D. F of B is equal to F. F of C is equal to F. It's like a...
Oh, nice.
It's just like this, you know? You get that this is an example of a mapping. Here's an easy one for you. F, let's say, is 0, 1, 2, 3. And that goes to 0, 1, 2, da 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 da. Keep going. Okay. Maybe this one goes up to infinity. So maybe f of 0 gives 0. Maybe f of 1 gives 1. Maybe f of 2 gives 4. Maybe f of 3 gives 9.
So F0, it can be 0 and 1, 2, 3, 4, 5.
Huh?
Each one. So
Yes. Yes. For each one. Yeah. Yeah, that's true.
So they just want us to draw this?
No, I'm just giving you the idea. So now we'll have a look at some more ideas with this and some questions, okay? So we can say F, for all my definitions, I'll say F goes from set A to set B. And A is called the domain. We know this word. B is not called the range. It's called the codomain. Okay? So, first definition. F is many 1. This means we can find an x and a y. Guys, do you know what this symbol means? This symbol here. You know this symbol, Ben? Do you know this symbol? This one?
What's this?
It means exists, is possible. Yeah? What's wrong, Gavin? Continue?
Yeah.
So f is many 1 if there exists. No, sorry. You know what? I want to call it something different. Exists x1, x2 in the domain and y in the codomain such that fx1 equals y and fx2 equals y. So what that means is there must be at least 2 that go to the same number. Then we call it many 1. Now I'll give you an example. Fx equals x squared because f1, or let's say f2, is equal to 4, but f minus 2 is also equal to 4. So we call this many 1 because you could have many x's but 1 y. You get the idea?
Yeah. What is ST?
Such that.
Oh.
Yeah. Continue. So the next one is f is 1 many. I'll write that in red. F is 1 many.
0.
Huh?
0. 0 just have 0.
Let me show you. So that means there exists a y1 not equal to y2, and they're both in B, and an x that's in A, such that y1 equals fx, and also y2 equals fx. So the picture here is like this. You have 2 here, and you have 1 here, and you could have 1 that goes to 2 different answers.
It's s square, x square.
No, square root. Square root.
Yes.
Square root.
Yeah, yeah.
So an example would be fx equals plus or minus square root x. 3. F is what have I still to do? 1 1. So that means do you know this symbol?
Right, but I don't know what this means.
For every. So for every x1 not equal to x2 in A, such that fx1 does not equal fx2. So an example here is fx equals ex. Because if you can never get the same answer, it's always different. If the x's are different, the answer is always different. You understand? Yeah, and number 4, what's the last one I have to do? F is many. So that just means F is both 1 many and many 1. It is both. So
Don't include the 1 1.
I did one more. Yeah. So like it would look like this. You would have 1 point that would go to 2, and you also have 2 points which would go to 1. Yeah? More words, I'm afraid. The image of f is fx. Oh, sorry. Oh, yeah, no, the image. Yeah. Is fx for all x in the domain. In other words, it's the same thing as the range. It's all the possible answers. So just to give you an example, suppose you have fx is real numbers to real numbers, and fx is equal to x squared. Okay? The domain equals OR. The codomain equals OR. But the image is equal to 0, infinity. Because of this, we don't get all the real numbers, do we? We only get the positives. So we can picture it like this. This is the domain. This is the codomain. We have all our points here. But the f only takes them to half of it here in this example. This piece here is called the image. You see, you don't get any negatives. In this one here, you get only positives. Okay. If the image equals the codomain, we say f is onto, or another word for it is surjective. So remember last time we said it's onto if the range equals OR. We said it's onto. This is the reason why. Because if the image is equal to the codomain, if it fills it up, we say it's onto. This function here, is this onto? No. It nearly fills it up, but it misses one number. What does it miss?
0.
0. This cannot equal 0. Okay, another definition. If f is 1, 1, we also call it injective.
You see the whole thing.
Huh?
Because the whole things can just.
Yeah. Injective. Yes, Ben?
Is many, many.
Huh? Oh, that's a different thing.
What is this?
What's what, this?
Uh,
That's the image of F.
it's different many.
Yeah, yeah.
Ah,
It's a new definition.
image.
I have a few things here.
One we also call injective.
Just another name for it. Mm.
So if image doesn't equal the code domain,
It's not surjective.
not subjective.
Last definition, I promise. If F is injective and surjective, we say it is bijective.
Can you give us an example?
Yes. This is bijective. Firstly, it's injective because x1 cubed never equals x2 cubed if x1 and x2 are different. It's also surjective because the image is equal to OR. It's okay? Lots of English today. Lots of English, right?
Easier than EAP.
Is it?
Yeah.
Let's do some examples now, okay? So let's look at A. Okay, have a look at A. Where's your book? Right. For question 1, I want to know, is it many ones, one many, or many many? So let's have a look at the first one. Is it many one? No.
It's many, many.
It's many many?
Yeah.
It's many.
Or
Here,
many.
I have to draw it. Look, let me draw it. So here we have AB, and here we have X, Y, Z. So HA goes to Z. HA also goes to X. HB goes to Z. And HB goes to X. So this is one many, and this is one many. But this, yeah, okay, it's many, many, isn't it? That's what you said somewhere. Right, what about the next one? Let's have a look. A, C, X, Y, Z. Okay. A goes to X. A goes to Z,
One many.
C goes to Y. No, not 1, 1.
Many.
One many.
One many.
Oh, many.
One many.
One.
Because this one goes to 2.
Yeah.
And you don't care about it doesn't change anything.
Okay.
This one's one many. You get the idea?
Yeah.
Yeah? Now, number 2 is a little bit harder because now we have functions. So, here, I want to draw you some graphs. This one is if it's 1, 1. This one if it's many 1. One many. And many, many. So if it's 1, 1, this should happen. If you draw a horizontal line, it meets only once, no matter where. Okay? If I draw it here, if I draw it here, it meets only once. Okay? Once.
But I just a line, linear.
Linear is 1, 1, yeah. And if you draw a vertical, it should also meet only once. This is 1, 1. Many 1 is like this, like maybe a quadratic. So if you draw a horizontal line, it meets more than once.
It's many one.
Yeah. Yeah. Remember, we gave the example earlier, didn't we? Where's our example? Many 1.
Oh.
See? We said it like x squared.
Yeah.
Yeah.
2x get
2 x's get 1 y.
Yeah.
And when you draw a vertical line, it meets only once. Okay, 1 many is like this maybe. When you draw a horizontal line, it's once, but a vertical line is 2.
So it can be okay. This.
Yeah? Yeah. And many is maybe something like this. When you draw a horizontal line, it's more than once, and a vertical line also more than once. Yeah? So, let's do some of these together. If it's, well, let's just look. Number 2, 6x plus 8. Which one is that?
One.
It's 1, 1.
Well,
That's easy. Okay. What about the next one, B?
so
Many
you
one.
can-
Many 1.
Yeah.
Why? Let's have a look at an example. 2x squared minus 4x minus 2. What's that equal to? You could change that into 2x, x. No.
Move the 2 in.
Oh yeah. X squared minus 2x minus 1. X minus 1.
Minus 2 or minus 4.
No, this doesn't have roots, does it?
Minus 4. Oh, I mean x minus 1 and square and minus 4.
Yeah, complete the square. Yeah, I think that would be better. So x minus 1 squared, that's 2x squared minus 2x plus 2 minus 4. Okay? That's fx. If you calculate f of 0, you'll get the same as f of 2. Because if you think about the graph here, well, I'm sorry, I did that badly. At 1, you have the minimum. So if you go to the left and to the right, you'll get the same answer. Let's check it out. F of 0 equals minus 2. F of 2 equals minus 2. So this is clearly many 1. Okay. What about the next one?
One more.
First one.
G? 1, 1? Are you sure?
G.
C, I mean. What do you think?
How to say? Oh. Is many 1.
Yeah.
Oh. Yeah.
Because if you draw a horizontal line here, you get 1, 2, 3.
Yes.
Yeah.
Yeah.
What about D?
Also.
No. D is 1, 1. Because look, you can write it like this.
What's the teacher? What?
You see, if you calculate this, it's never 0. In fact, if you calculate it, you get it's always positive, increasing. The derivative is equal to 3x plus 1 squared. So that's sneaky. Yeah? What about E? What about E?
I think is 1 1.
Yes, it's 1, 1.
Like this.
Yeah. Now, if we want to check, this is how we can check, okay? What we do is we,
Why?
like this. Well, you assume that if x1 doesn't equal x2, then you could find gx1 equals gx2. So assume that it's not 1, 1. Assume it's many 1. It's possible. Okay, so let's see what happens. 1 over 12x1 plus 12, that equals 1 over 12x2 plus 12. Can we find an x1 and an x2 that are different, but these are the same? Well, if I multiply, I get 12x2 plus 12 equals 12x1 plus 12, right? And I can get this as x2 equals x1. So if these are the same, it's only if these are the same. So this is not possible. It's not possible, so it must be 1, 1. Okay. I'll give you another example. Let's do a hard one. A really, really hard one. Yeah.
If we don't know the D is x minus 1
Cubed.
How
My advice is to calculate the derivative.
so
Because if it's many 1, then if you calculate the derivative, this value to the left and this value to the right should be the same. You could do it this way. But I'm going to show you another way, okay? I'll show you another way. L. So what we'll do is we see if we can find any x1 not equal to x2 such that fx1 equals fx2. So tell me, if we can find two different x's, but fx1 and fx2 are the same, then what have we found? Is it 1, 1 or many 1?
Anyone.
Is many 1, yeah. And if we can't do this, then it must be 1, 1. Okay, so let's see if we can do it. x1 squared minus 4x1 minus 5 over, oh my goodness, maybe this is too hard. X1 squared minus 4x1 plus 3. Could that equal x2 squared minus 4x2 minus 5 over x2 squared minus 4x2 plus 3? Okay, the first thing I think I'll do is I'll factorize. What are the factors here? X1 minus 5, x1 plus 1, thank you. x1 minus 1, and x1 minus 3. No.
Oh,
Yeah, don't confuse me. And this is x2 minus... x2 minus 5, x2 plus 1, x2 minus 1, x2 minus 3. Now, choose x1 equals 5 and x2 equal minus 1. Does x1 equal x2? No. But if you calculate here, f of 5, if you put 5 in here, what do you get? You get 0. And if you put minus 1 in here, what do you get? 0. So we can see that f5 and f of minus 1, they're the same. They're both 0. So therefore this is many 1, because we've shown that if you have minus 1 and if you have 5, they both go to 0. Yeah? That's a difficult one. Hard, yeah? Nah, not too bad. Oh, look how tired you are.
Like say it's so much medicine to make me sleep.
You have sleepy medicine.
I think that every medicine will make people.
I think most do. Okay, let me give you some to try. Yeah, I'll give you 4 and 4. Okay, so in question 1, I want you to do I, J, M, double M, and O.
IJ
IJMO.
is 1. Okay.
And in question 2, I want you to do M, M, N, U, Y. Be strong, girl. If you try those for a few minutes, and then we'll go on to the next lesson. The next lesson is easy. Yeah.